Today we're going to talk about race conditions. This slide gives you a couple different definitions of a race condition, but essentially what a race condition is the output of a program or multiple processes running will depend on the order of operations or when those processes get run. And we'll look at a few examples. So again, you can read these few definitions here. Everything deals with the sequence of events or timing of events. And then the last one deals with concurrent threads or concurrent processes, which is where we'll really get into the race condition issues when we talk about those in more detail. Let's look at an example, a basic example. Let's say that a couple wants to deposit and withdraw money from a shared checking account during lunch. So the husband wants to withdraw $400, but there's currently only $200 in the account. So the wife needs to first deposit $500, so there's a little bit extra, and the husband can withdraw the $400. And you can see already, thinking about this, how the order of operations is going to dictate the outcome. So if the husband gets to the ATM first, $200, what's going to happen? Insufficient funds. The money is not available for the husband to withdraw $400. But if the wife gets to the ATM first, she deposits the $500, giving us a balance of $700. So now the husband can go and withdraw the $400 successfully. So you can see the sequence of events dictates or determines the outcome. So now let's look at a programming example. Let's say that we have a program where we're going to read the value of X, either from a file or a database or something, and we'll assume that X has a current value of 10. The program will add 5 to X and save the new value, so 15, and then we're going to print the value of X, which will be 15 for a general run. But let's say that we have 2 users that run this program, so we have 2 different processes running the same code. If the processes run sequentially, then process A is going to read the value of X. It will add 5 to X for 15 and print 15. Now process B runs. Now it reads X. It is now 15. Process B will add 5 to X and store the new value of 20. So now when it prints X, it's 20. And that's what we would expect. If we have 2 processes running that same code, essentially we're adding 10 to X to get 20 after both processes finish. But what happens if the processes are run concurrently? Let's say process A runs, reads the value of X, 10. Now the operating system interrupts that process. The process has to leave the CPU, gets put back on the queue because it just got interrupted, so it's in the queue. The operating system is finished and reads from the queue, but now process B was in front of process A on the queue. So process A read X, process B runs now and it reads X, which is still 10. We add 5, we get 15. Now process B finishes, it prints 15 and finishes, and process A gets the CPU again, but it already read 10, so it adds 5 to get 15 and prints 15. So instead of getting our result of 20 after 2 processes run the same code, we end up with both processes having 15. This is a race condition. It's a race to see which process reads X first and adds 5, and if they're done sequentially or concurrently. So what are solutions for eliminating race conditions? So one solution is to use locks and create mutual exclusion. There's 2 different types of locks, a read lock and a write lock. A read lock, multiple processes can have read locks at one time for the same data or the same record in a database because we're just reading the information. 50 processes could read that information and it's the same, it doesn't matter. The write locks are the ones that have to be exclusive. Only one process can have a write lock at a time for data or a record in a database or a table in a database, because if we're going to change that value and write a new value, we want the new value to be sent to all the other processes, or for any new process to get the new value. We don't want one process overwriting the value of another one. So we need to have one process with a write lock at a time. So what we want to do is before a program writes it, they're going to get a write lock. But you have to be careful how you do the locking. What we want to do in this case, for our code here, we want to read X, add 5, print. So what we need to do actually is, one solution is to do the write lock before the read. Even though we're just reading, we're going to do a write lock because the next thing we're going to do is update and write the value of X. Now you have to be really careful how much code you have between the write lock and when it releases it, because you don't want it blocking out too many other processes for too long of a period of time. So we're going to do the write lock, read X, update, write X, release the write lock. And then we can print our value of X, which is fine. That'll be 15. But you want to be careful how much time is in between when you get the exclusive write lock and when you release that. Okay, when you have an exclusive write lock, no other process will be able to access that data, even for a read lock. It's an exclusive lock. One of the issues, though, is the possibility of what's called a deadlock. And a deadlock is a situation where two processes are waiting for each other to proceed, so neither process can proceed. So they're both locked, and neither will make progress. That was the situation back here. If we consider this, if we did a read lock now, so we read X, we put that around a read lock, and then when we're going to write X, we just put that part of the code around the write lock. What happens is process A will do the read lock, read X, and then relinquish the read lock if we relinquish it there. And then process B will read X, read lock, read 10, relinquish, right? But now they've both read 10 still, so we still have the race condition. So what if we put a read block around the entire length of code? Let's do a read block. So process A will do a read lock, read 10, don't relinquish it yet. So now process B does a read lock, which it can because multiple processes can have a read lock, read 10. Now we do a write lock, but we can't get the write lock. We're going to block there. We can't get the write lock until process A relinquishes its read lock, and process A won't relinquish the read lock until it gets its write lock. So they're both going to be in a deadlock situation. Both of them have a read lock. They're not going to release the read lock until after they do the write. They both need a write lock, which they can't get because the other has a read lock. Remember, the write locks are exclusive. So that's why I said originally that we'll put the write lock around the statements read X and the assignment statement. So we do the write lock around that block and treat it as a transaction. In order to avoid the deadlock situations, another solution is an atomic operation, to create an atomic operations, which is sort of what we did with the write lock. Atomic operations are used in concurrent programming, and especially with multi-threaded programming. And with the atomic operation, it groups the operations as one. So it'll group the read X, the X plus 5, and the assignment as one, and other threads will see them as completing simultaneously. So you can't have a partially completed transaction. You can't have a context switch in the middle of an atomic operation. So when we get to multi-threaded, we'll talk a little bit more about atomic operations, but that's a very nice solution to avoid the race conditions. So the example for that, you would have your atomic operation similar to our exclusive locks, but there's other issues with locks with blocking out. But we have the atomic operation, we read the value, we do the addition and the assignment, and then we end the atomic operation. So we saw a definition of a race condition, we saw a real-world example and a programmatic example, and discussed a few solutions.